All right, that's time. Thank you. Thank you, thank you. Okay. Sorry. Is that extra? Oh, there's two. Okay, thank you. All right, anyone else? All right, so on that quiz, just draw it up here real quick. We have a function that's doing something like this. So this is the function f, and you're asked, part A, to figure this out. All right, so who wants to tell me what this means? Go ahead.
The limit of x, if I'm saying that right, approaching 2 from the left side, what's it equal to?
Yeah, what's the function doing as you approach 2 from the left? So here's 2. If I'm on the function but I'm on the left and I'm coming in towards this line, what's the value of the function approaching? So it's approaching a y value of 2. That's it. B, what's the limit as x approaches 2 with the plus sign, right? So someone else, what does that mean? It's 1, yes, but it means coming from the right side this time. So you're still approaching an x value of 2. This time you're coming in from the right, and you can see that your y value, your height, is approaching the value of 1. Even though you never actually get to it, it's 1. Part C, same thing except there's no plus or minus up there, which means that what? You have to look at both sides, and you need these both to be what in order to put an answer here? The same number. And if they're not, you put does not exist, which you put as in D and E, or you write does not exist. You can put undefined, but most calculus books reserve does not exist when you come to talk about limits. So does not exist. And then part D is just what's f of 2. And that means now you go to the value 2 and you actually say, does your function, is it defined anywhere here? Yes, it's defined down here to be 0. That's it. That's the quiz. That's just a very basic, you know, were you able to watch the video and make sense out of it type thing? Okay? And so we're going to move on. And what I want to do is I want to pick up at the end of the video that I asked you to watch. There was an example that I said that I would do in class. And it was kind of backwards from everything that I had done in the video, because in the video I gave you a bunch of graphs and then talked about, you know, what's the limit coming in this way, and this one's kind of a reverse. I give you all the information about the limits, and then I ask you to draw a graph that does that behaves that way. So first thing, everyone should have a different graph. Nobody's graph is going to look exactly the same as everyone else's, but they will all have these same characteristics, right? So let's start with the first part. I'm going to draw a big old XY axis. Where am I? Negative 2. So I need to draw a function that satisfies all of these 7 criteria. So let's start with the first one. I need the limit as x approaches negative 2 of the function to be equal to 3. So I'm going to go on my x-axis. I'm going to go to negative 2. And I need the value to be approaching 3. So let's see. Let's start with this table. Anyone on this table want to help me? Tell me what I need to draw in order to make that first thing.
Would it be a line coming from over here?
How high? That's our x value. Right, x is approaching negative 2.
It goes to 3.
Okay, so 3 high, right? So 1, 2, here's 3, right? Okay, so what that first part means is that as we approach negative 2, right? As we approach it, our function's value should be approaching a y value of 3. Which side does that need to be true?
Left and right?
Left and right. Because notice the little negative sign, there's nothing above the 2 on the top right. Okay, so the negative 2 in there is kind of tricky a little bit. Don't look at that. You're looking at the top right for a plus or a minus. If it's not there, then that means you have to look both directions. So I'm going to go up here to 3, and what I'm going to do is I'm going to draw a hole. And what I know is that from the left, I come into that, and from the right, I come into that. Do you agree that that picture satisfies the first criteria?
Yes.
Yes? Now, I left it open because the limit tells me nothing about what's happening at negative 2, does it? So, let's leave it. Oh, but look at part 2. What does it say? F of negative 2 is 0. So the value of the function at negative 2 is exactly 0, so now I can fill a dot in there. So I've got 2 of the criteria done. We good? Questions? Okay, the next criteria, it's kind of hard to see that, but there is a little negative sign here above the 1. So who wants to tell me? Go ahead, Edward. Ed. Okay, so I'm going to draw 1 here from the left. So from this direction, I should be at negative 1. So let me move down. There's a what? You want to put a little hole here and then just draw something coming out the left side?
Kind of scoops down and goes back up.
Yeah, that good? I mean, it doesn't really matter what it does as long as it comes in, right? Like someone else could draw this. Someone else could draw that. As long as you're coming in from the left, it's headed to negative 1, yes? Okay, so I'll just leave that one there. All right. What about the next part? Saying as I approach 1, go ahead.
It's you approach 1 from the right to the equal to 2. So the 2 would be on the y-axis.
Y-axis?
Yeah.
You want me to draw, what do you want me to draw?
Just a hole.
A hole again?
Mm-hmm.
And then right side, just tail it out somewhere like that? Okay. Everyone seen this? We're going to put this all together in a picture at the end, all right? But this satisfies that the function, as you approach 1 from the left, it's going to negative 1. As you approach 1 from the right, it's approaching positive 2. What is f of 1? 2. So that means I can do what? Color that circle in up here. So now I've taken care of, what, the first 4 criteria? Okay, now as I approach 4 from the left, this is the 5th criteria here. 4 from the left. So here's 2, 3, here's 4. So as I draw my function from the left this way, where is it headed? To positive infinity, which means straight up. So that means I have almost like a vertical asymptote here. And my graph goes like this and heads towards positive infinity. As I'm coming into 4 from the left, my graph is headed up to positive infinity. Does that make sense? Let's see. How about this table? How about the last criteria, or the 6th criteria? Anyone here? What I should draw? Justin, Jared, Daniela?
So the function is equal to 0 when you're approaching it
From the right. So what do you want me to draw here? Tell me something to put on this graph that would...
you put a closed circle at 4.
Okay. Do you mean close like fill in or not fill in? Filled?
Because it's equal to 0.
What do y'all think? No? Remember, the limit on part 6, right? The limit tells you what's happening as you get close to 4. It never tells you what's happening at 4. So you will always leave this open unless they tell you later how to define this point. So we're going to leave it open, but I will need to come towards that from the right so I can just tail it out like that. Something like this. And the last part says, look, at 4, your function's what? Undefined. That means I'm never going to fill in anything on 4. I'm just going to always, always have it undefined. And that's it. This satisfies all the criteria. But I need to draw a function. I mean, this doesn't look like a function. It looks like a bunch of crap all over the place, right? So functions are nice, and let's just draw a nice smooth function. Let's make sure it passes the vertical line test. Remember, all functions have to pass the vertical line test. So what I'm going to do now is I'm just going to come in here and connect things together. So like over here, out this way, I don't really care because I don't have any information about that. So I'll just put an arrow. It goes out that way. I don't know what it does. And then here it came and jumped down here and had the dot and came back up. And then from here, I've got to get to this piece, right? So I don't know. I'll do something like this. Connect those together. And then over here, this piece has got to eventually get to there. So just, connect them together, and then maybe out this side I'll get crazy and I'll make it go down. Who knows, right? So that's my picture. Everybody's picture is going to be different. All the red parts are up to interpretation pretty much. But everyone should have the same characteristics in terms of the limits and where things are defined and undefined. Understand? Okay. Yes?
So when we know it's open and closed circle, what is open circle?
It's pretty much always open if you're looking at a limit. Okay, it's always an open circle if it's a limit because, like, look at 6 again. It said that as I come into 4, here's 4, as I come in from the right, the function is headed towards a y value of 0. But it doesn't tell me what happens when I actually get there. So I'm not allowed to fill this in with a dot based on that information in part 6 because that doesn't say at 4 you're 0. It says near 4 to the right. It's headed towards it. So I put an open circle just to give myself somewhere to go, right? Like if I didn't put a circle here and I drew it like this, then you can't really tell. Am I saying that at 4 it's 0? Like, it's hard to tell because I'm drawing, it's only as wide as my marker, Like, so is there a hole there or not? Well, let me be very clear. Yes, there's a hole there. There's nothing at 4. Now, if number 7 would have said this, right? If number 7 would have said this, then I would go to 4. It would be 0 high. I would fill the dot in. If that's what number 7 said. But number 7 said it's undefined, so I never filled anything in. Does that clarify a little bit? Okay. All right. Any other questions on this? Yes?
I was just gonna, it kind of went on what he was talking about. How come you cut it in number 3 if it was approaching 2, but it's...
Because the next piece of information,
Oh, okay, yeah, my bad. You're right.
number 4,
Yeah.
right? Part 4 says at 1, go ahead and fill it in 2,
All right, nice. Yeah.
right?
Cool.
So if all you had was limits everywhere, if all I had given you was limits, then all of these would have been open because you don't know anything about what's going on there. There was an analogy I heard once that kind of helped a little bit when I was a student. If you've ever looked at like a window, well, I could probably do this better with 2 pieces of paper. You ever seen like a window in a house? You have something like that, right? And you have, this is like a piece of metal or a piece of wood, right? And then you have like the different panes of glass. Yes? Okay, so imagine that there's a function, okay, on the other side of this window, and you're looking out at it, and the function does something like this, okay? Let's just say that. So in college algebra, what we're doing in college algebra is we're actually looking at the function's value at a single point. So we're always looking at a single value and we're saying, oh, okay, right there, it's that little red piece, right? And then I come over here and look, hey, at this red piece, it's down here, right? In college algebra, we're always looking at single places. But in calculus, what we're doing is a little different. What we're doing is we're opening up this window, right, like this, and ignoring the middle. And saying what's happening as we come into that middle piece. And that middle piece is now covered up with the window, we can't see it. So we don't care what's happening here. It actually doesn't matter to us at all. What matters to us is approaching from both sides. Does that make a little bit of sense? Okay. Any other questions? Okay, pretty much everything that we've done up to this point with the idea of a limit has been visual, right? It's always been me giving a picture, saying, hey, look as we come in from both sides, or in this case, I gave you information and we drew a picture. But at the end of it all, we want to be able to take limits and never draw pictures. We want to be able to take limits mechanically by hand and figure out what's happening. So that's what the next section is over. It's about calculating limits. So that's what I just said. Pretty much we have pictures, but now we're going to try and do these by hand. And what we're going to see is this is going to require this will require significant amounts of algebraic skill and tricks in order to calculate limits. So it's one thing for me to draw a picture and say, hey, what's happening as x approaches 2? From the left, from the right. That's one thing. But how about I just give you the function, f of x equals this, and then ask you what's happening? Without the picture, how are you going to be able to determine, right? So that's what we're going to look at. So before we can actually do it, we have what are called the limit laws. This is a little too big. These are all in the book. I don't recommend you sit here and try and copy these down. These are all in the book, but I do want to just skim through what they're saying. All right, first of all, imagine that you have a function f and a function g where the limits as you approach a exist for both of them. So I will give you a picture of what we're saying here. You have some value a, you have some function f, and the limit exists at a. That means that it's approaching the same place from both sides. Because remember, if I don't put a plus or minus on the top of that a, that means you have to look at both sides. So this is a picture of what I have so far in the conditions. The next one says you have the same exact thing for a different function g. So g may be going to a different place, but it also has the same characteristic that it's going to the same place from both sides. All right? Two functions, f and g, where the limits at a both exist. With me? Okay, let me throw something over here. I'm just tacking this on to see if y'all are understanding this or not. So what's the limit as x approaches a of f? 3. The limit is as x approaches a of g? 2. Right? From both sides, it's approaching 2. All right. So the limit laws say, if you start with two functions that have limits at a single point, you are always allowed to, first, if you have them added together and you're trying to find the limit, that you can do the limit separately. So you can do the limit of each one separately instead of having to combine them and do the limit all at one time. So it allows us to peel functions apart. The next limit law 2 says you can also do it for a difference. If you have subtraction between two functions, you can just do the limit of one, do the limit of the other, subtract the two answers. The next one says if you have a constant in front of a function, that you can ignore the constant. Look, bring the constant out in front, figure out what the limit of the function is, and then multiply that when you're done. So these are all like arithmetic things that we're allowed to do with limits. They've been proven. That means that mathematicians have a way of proving that these are all true. We're just going to use the results. Look at the next one. This is very nice. It says that let's say you have two functions that are multiplied together, and you're trying to figure out what happens when you take a limit. That you can actually peel those apart into two different limits, take the limits individually, and multiply the two answers together. We'll be praying for that, or we'll be wishing it was that easy later. It's going to turn out to not be that easy later. And then this one is the same rule, but for a quotient. So if you have two functions being divided, you want to see how they're behaving, you can look at the top and bottom separately and figure out how each one behaves, and then divide that answer. This is another one that's very important. If you're looking at a function that's being raised to a power, sine cubed, the fifth root of tangent x, anything being raised to a power, that you don't have to deal with the power. You can actually take the limit and push it into the function, with the function, figure out what that is, and then just raise it to the power. That's a very nice property of limits, that you can pass it through a power. Does that make sense when I say it? I'm passing it through the power. The limit of a constant is a constant. I'm going to draw that one on the board. I'm going to give you an example of a function that's a constant function. There's a constant function, right? If I draw that function, then if I go to any point, right, it doesn't matter where it is, and I say, what's the limit as you approach A, what's it going to be? 3, no matter where I go, right? So it actually does not matter where I am, the limit's always 3. So if you have the limit of a constant function, which is just C, the answer is just a constant function. How about this next one? The limit as x approaches A of x, so this is a specific function also. What is the f of x equal x look like?
Isn't it just like a diagonal?
It's the diagonal. We call this the identity, right? That's f of x equals x. According to this, the limit as x approaches A is A. Well, what's the value of the function here? If I plug in A, what does this function spit out? If you plug in A, it spits out A, doesn't it? So what would be the limit as I approach A? It would be A, right? If I move A over here, I'll call it A sub 2, then the height of it is also A sub 2, and so you're approaching A sub 2 from both sides. So basically, no matter where you move, right, where you move the A, the x value is always going to change to that. So I want you to almost see it like this. All you're doing is saying, hey, let x turn into A, right? All right, turn that into A. What does it become? A. It's really that simple. You're doing what we call direct substitution. You're just plugging A in for x. This is exactly the same way. Let x turn into A, and then x to the n. So any power function will just become A to the n. Next one's the same thing except square root. And then the last one is you can pass a limit through a root. So this is kind of like the one before where I said you could pass it through the power. Here you can pass it through the square root. So all of this seems like really kind of weird until you actually do some examples. But I'll cite these limit laws as we go, all right? Now we have a nice thing called the direct substitution property. So it says, given a function, the implied domain is a set of values for which that may be plugged into the function without causing the function to be undefined. We talked about implied domains before, right? It's those values of x that are kind of understood to be okay. There are certain values that are not okay. So just make sure we understand that, what implied domain means. And now this is the direct substitution property, very important. If f is a polynomial function, that's a big group of functions, isn't it? That's a big class of functions, polynomial. If f is a polynomial, if it's a rational function, that's another huge classification of functions. If it's a trigonometric function, sine, cosine, tangent, right? Secant, cosecant, cotangent. Another big group of functions. If it's an exponential function or a log function, any of those, then as long as A is in the implied domain, as long as the number we're trying to plug in is in the implied domain, we have direct substitution, which means we can just take x and replace it with A. I'm going to give you an example on the board right now to show you that property in action. So let's look at, as an example, what is the limit as x approaches 2 of x squared plus x minus, let's say, 6 over x plus 3. Let's take a look at this right here. So there was a limit law, right? A limit law that said that if I had two functions in division, right, I could actually split this up and look at the top one and bottom separately, couldn't I? All right, I'm going to write this out. We're not going to be doing this throughout the semester because this is way too tedious to have to write this out over and over. But I want you to see how this all works. So there's a limit law that says I can do that, right? Then, isn't there another limit law that says that if I have addition or subtraction between things, I can split them each up into their individual limits? So I could turn that into limit x approaches 2 of x squared plus another limit as x approaches 2 of x plus another limit as x approaches 2 of negative 6. So I did 3 separate limits here, right?
What does it subtract?
You could do minus and make this a plus. Is that what you're asking? Yeah. You could leave this as a minus and make that a positive 6, or you could do plus a negative 6. Either way. All over. And then on the bottom I have 2 terms, so I can go limit x approaches 2 of x plus limit x approaches 2 of 3. So I've used the limit law to split a quotient into 2 limits, and then the limit law again that splits sums and differences into individual limits. And then we can look at each one. This one right here, according to limit law, which one is it? 9, says that if I have x to a power, all I have to do is replace that x with the a. So this is going to become what? 2 squared? Which is 4. So notice I'm going to put 4 here. Notice I did not write the limit anymore. That's because I've taken the limit. I've said what happens when x gets really, really close to 2. This number gets really, really close to 4. Okay, what about this one? That's just 2. That's limit law 8, isn't it? It's direct substitution in there. 2. And then what about this one?
It's a constant?
That's a constant, negative 6. So this doesn't change anything, does it? That's limit law 7. So minus 6. All over.
2
2
plus 3.
plus 3. So what do you get? You get 0 over 5, which is 0. So your limit is 0. Question?
How do you get that for the numbers? I don't understand that part. 4 plus 2 minus 6.
Right here,
Yeah.
replace, I'm using limit law 9,
Okay.
right? A is 2, so this becomes a squared.
Oh, okay.
So 2 squared is 4.
Okay.
It's not, we're not trying to make this tricky. It's just, right now, we're just replacing x with the value. That's all that's happening, right? Yes?
So we won't have to write all that down, we just.
You don't. You don't, because look, that's what the next thing that we were talking about was, right here. I said if it's a polynomial or a rational function or any of those things, then all we have to do is just replace it. We don't have to write all this down. So this is the long way of doing it. Now let's look at the short way, which is the direct substitution property, note 1.4.4. So come back to this and say, is this whole thing together? Is this whole thing a rational function? Is it? Yes? Okay, what's its implied domain? What's the one number we can't have here? We can't have negative 3. So in the domain of this, we know that it's the set of all x's such that x cannot be equal to negative 3, right? That's our domain? Domain is all x's except negative 3. But where are we headed to? Where are we actually investigating in our picture? At 2. Is that negative 3? No, we're not even close. If we're moving around looking at the graph, opening that window up, trying to see what's happening, we're not even near negative 3, so we're not worried about it. So because of that, because the a is within, as long as a is in the implied domain, as long as this 2 is in the implied domain, which it is, then all we have to do is direct substitution. All I have to do is just replace all my x's with 2's, and I'm done. So So this would be equal to, what, 4 plus 2 minus 6 over 2 plus 3, so 0 over 5, which is 0, which is exactly the same thing we got when we wrote all the limits out. Understand? This is a very, very nice result. But this calculus cannot be this simple, right? It can't be where all you're doing is just plugging numbers in. I mean, that's what we did in college algebra. So what would be the difference? So let me just change the problem. What was the problem that we had? Okay, let me try that then.
Give you 0 over 0.
Yeah, you can't do this, can you? Because if you try and plug -3 in, right? Let me just try this. So I'm going to do this in a different color to let you know that what I'm doing here is I'm trying direct. Okay, I'm trying direct substitution right now. And you should always try direct substitution first. And if it fails, and we do something else. But try it first, because if it works and you get 0 like we just got, right, 0 over 5, then we're done. The answer is 0. We'd be finished. But here, if I try and plug it in -3, what's that, -3 squared, 9 minus 3 minus 6 over -3 plus 3. This is 0 over 0. And this is what I told you calculus was about, right? When I was trying to introduce you to the idea, is trying to get around this. So what I'm going to do is I'm actually going to graph this for us. Okay, it's x squared plus x minus 6 divided by x plus 3. And here, I did. Yes, that's not good. There it is. Okay, there's the graph. Everyone see that clearly? Looks almost like a line, doesn't it? What's happening at -3? According to this up here, what's happening at -3? What should we have at -3? A hole. We should have a hole. But a computer is not going to show you the hole. Just like when you graph this on your graphing calculator, it's not going to show you the hole. Why? Because they don't. So you may think this is a straight line with no holes in it, but there is a hole. So what I have, where the hell's my thing? There it is. Okay. I can move this red dot along here. What x value should I stay away from? -3. So you see my x values right here. I know it's hard to read that. It says -1.75, -2, -2.75. Here we go. Oh, let me go back one more. Boom. Okay, my computer just freaked out. Okay, because I'm asking it to plug it in. It's getting 0 over 0. And look at what it's saying down here. You know, infinite expression, intermediate expression, complex infinity encountered, error, abort, eject, right? I mean, the computer's freaking out. But it's pretty clear that when I was getting closer to -3, right, that my function was headed somewhere, wasn't it? I mean, there is a circle here that the computer's not willing to draw for us, right? So that limit should exist, right? There should be some numerical value I'm headed towards in both directions. You can kind of tell what it is from my picture, right? Can you tell what it is? -5. But you're cheating, you're using my picture. I'm not allowed to use my picture. So what if you can't use that picture? How are we going to know that this thing is headed towards -5? Understand? Okay, so here's how we do it. Anytime we run into this, okay, anytime we run into this, then what we will have to do, okay, so when faced with 0 over 0, you must use algebra or some trick. And Cal 1 is full of tricks. Right? It's full of tricks. It's one of those things where I'm going to show you something for the first time you've ever seen it. And you go, wow, I would have never thought of that. And I'll agree with you and I'll say, but now you know. And so now you can use that trick anytime you need to use it. Yes?
Couldn't you just do like the limit of x going to like 3.1 or negative 3.1?
Yes, okay, so that's a good question. Why not just take a number really close to negative 3.1 and plug it in? We could do that. We could actually probably make a table where we take things getting closer to negative 3, like negative 2.9, and then get close, like negative 2.99, then like negative 2.999, and then like negative 2.9999, right? And you could keep doing this, and you would probably see a pattern over here of them getting closer and closer to negative 5. That's probably what would happen, right? And then you could also do another table and come in on the other side. Because right here, if this is negative 3, negative 2.9 is on the right side of it. And then the next one's closer and closer and closer, right? So this would be approaching it from the right. To approach it from the left, we'd have to do like negative 3.1, negative 3.01, negative 3.001, negative 3.0001. I keep doing that, but doesn't this seem like it would be a pain in the ass? I mean, just to do this over and over. Like you have to plug each one of these into this. Calculate it, right? But this is an approach. It's just too tedious. Maybe if we just do some algebra first, this will turn out, it'll spit out our answer, maybe. So here it comes. Look at the original limit up there. What do you know about that numerator? It factors, right? It's a quadratic trinomial. So would you agree that this is the same as, that's an arrow, sorry. Try that again. Okay, negative 3. It factors to be this, right? And look at that. Look at that. Isn't the part that caused the problem about to cancel? Now, you always have to be careful because back in college algebra, hopefully this was stressed to you. When you take an expression and you cancel factors like this, you are always allowed to do that. As long as you put a little asterisk on the side that says, I'm doing that as long as you allow, as long as I promise you that x will never be equal to negative 3. I have to make you that promise. Because if x is equal to negative 3, then this whole thing is undefined. By canceling these, you're kind of eliminating that problem. So I have to promise you I'm going to cancel, but remember that x can't be negative 3. Okay, so look what's next. Canceling it, but I'm saying to myself, x can never be negative 3, right? So this expression becomes this. I cancel, tell you x can't be negative 3 though, and then I write this. What is this equal to? Negative 5. How are you doing that? You're replacing x with negative 3, aren't you? But I just said x can't be negative 3. So why are you replacing it? Well, because you have to understand what the limit is saying. The limit is not telling you that this is negative 5. It's telling you what? It's approaching negative 5. It's getting closer to negative 5. See, x approaching negative 3 is not the same as x equaling negative 3. So imagine now at this point, you could do your analogy here. Plug in negative 2.9. Plug in negative 2.999. 2.99999. And these get closer and closer to what? Negative 5 without getting there. So negative 5, when we say that the limit is negative 5, we're not necessarily ever reaching it, but getting closer. But that's the same result that we would get off the graph, isn't it? Negative 5? So all that required was us to be able to do a little algebra. As you might imagine, the algebra is going to get harder, right? But that gives you some idea of how we can attack something like that. So I'm going to do some more problems. I'm going to page 44 in the book. I'm going to do some evens. All right, so the first limit that I showed you, right, when this was 2 in here, what did we get as an answer? When that was a 2?
0.
We got 0 over 5, which was just 0, right? Did we get in that problem 0 over 0? We didn't, right? So that's when direct substitution works the best, when it just spits out a nice number. This was your first example where we got 0 over 0. 0 over 0 is going to be the theme of the rest of this section, all right? So how about this? Limit. This is an example. H approaches 0 of 2x plus h cubed minus 8 over h. So I've switched some variables around. I'm using h instead of x. Okay? It's a dummy variable. We don't have to use x. So the first thing I'll do is I will check direct substitution. Right? Check my direct substitution to see whether or not I'm going to have a problem or not. So let h become 0, right? If h is 0, you get 2 cubed, which is 8 minus 8 over 0, which is 0 over 0, which is not a good thing, right? Which is not a good thing. On a quiz, on a test, if you put here, if you say that that's equal to 1, or if you say that that is equal to undefined or something like that, you will miss major points, because that means you're missing the entire reason we're sitting here right now, is that we're trying to get around this, trying to figure out if there is a numerical solution for this. So look at that while I graph it. Tell me if you can think about how you might attack that algebraically. And just think about it for now. Don't answer out loud. I'm going to graph it though. And this is the graph right there. So from the graph you can tell, I should probably zoom this out a little bit. We're approaching 0. So I switched to x so I could graph it. But can you tell from this graph that at 0, it looks like the graph is headed to the same place from both sides? Do you all see that? But we know that you can't plug 0 in. The computer's not telling us that by the picture. So does anybody have an idea? I'm going to move this to 0. It's going to freak out. There it goes. Freaked out.
Could you follow it?
You mean like multiply this all out?
Yeah.
Sure.
And then cancel stuff out.
Yep, absolutely. What do y'all think? Yeah? Okay. Any other ideas? I mean, that's correct, but any other ideas? I'm open to anything that's legal. Does anyone else see something here? That numerator?
The difference of 2 cubes?
It's a difference of cubes. So you could also factor it using a difference of cubes formula. You could do that too. Either way. I'm going to go with the first way, just multiply it all out first. Maybe we'll get lucky. So what happens if you take 2 plus h and you cube it? That's 2 plus h times 2 plus h times 2 plus h, right? You have to do all that multiplication. So 2 plus h times, what is this, 4 plus 4h plus h squared. When you do 2 of these together, and then you have to go 2 through everything, h through everything. So what would you get? Anyone know what all this multiplied out would be? 8 plus, what are you getting? 8h?
Yeah, 8h
8h?
plus 2h squared.
2h squared? Yeah, I think it's going to be a little more than that. Hold on, I don't know about this. Plus h cubed? So let me check it. 8, 8, 2. So you have 8 plus 8h plus 2h squared. Then plus the next one, 4h. See, 4h plus 4h squared plus h cubed. So I think you have, what, 12 h's? Not. So this is 12 h's. And then how many h squareds? 6 h squareds. And then over h. Right. Does everyone understand algebraically what you'd have to do here to expand this out? Okay. That's just this part right here, isn't it? What do I still have to do with that? Subtract 8. I had forgotten to put that there. And that's a really good thing that just happened with that minus 8. Because it's going to take this 8 out, right? And now, doesn't everything that's left have an h?
Yeah.
So you can factor an h out of the top. And that'll leave you with 12 plus 6h plus h, was that? Yeah, plus h squared, and that's it, all over h. And then you can cancel the h out. And we're almost there. You don't need a factor. You can just apply the limit now. Because, see, what you no longer have is a fraction, right? And so you're not going to get division by 0 no matter what. So you've eliminated the problem. The problem was the division by 0, and you've canceled that out. So now let your h approach 0. What happens to 6 times a number that gets really small? This is going to go to 0 also, right? This is really 0, like really small squared is still really small. So this is all really going to 0. And so all you're left with is 12. So on that graph, you can tell, can't you? Can you see that it's 12? This is 5, this is 10, 11, 12. So yeah, looks like from both directions, the graph was headed towards 12 as you approach 0. But there's a hole on the graph. The computer's not showing it. Y'all okay with that? So far the algebra has been pretty simple, right? I mean, nothing too extravagant here. How about this? How about the limit as x approaches 2 of 1 over x minus 1 over 2 over x minus 2. Now we're getting somewhere.
You just try plugging it in first.
Yep, always try your direct substitution first. What do you get here? You get 0 on top, because 1/2 minus 1/2, you get 0 over 0. And that means you're going to need to use some algebra or a trick, right? Something. I haven't shown you a trick yet. Everything's been algebra up to this point. We haven't needed a trick, I should say it that way. So look, in the previous two, what we did was we got the bad thing that caused the division by 0, we got that to cancel. Like in the previous one, it was the h, right? We got the h to go away. The one before that, we had the x plus 3 down on the bottom. We got it to cancel. So what we really start to think about is, can I get the x minus 2 to cancel? Can I get it? How do I get it? It's not straightforward. It's not just right now I can cancel it. But what can I do? When you see complex fractions like that, how can you simplify a complex fraction? That's right. You make the numerator into one fraction, so you can collect these two together, right? Can't you? Get a common denominator?
2x.
So if you collect these two together, the common denominator you said was 2x. What would the new numerator become?
0.
Well, don't plug in yet. Just algebraically when you put those together. What? 2 minus x. I don't know if I need to show that step because I don't know where you all are here in terms of your algebra.
And can you flip it, put over 1?
Can you multiply 2x?
Yep, yes, and what?
Multiply x minus 2 times 2x?
I'm not sure. Like, what? Do it?
Can you multiply the two last ones? 2x minus x minus 2? That 2x right there?
Sorry. This 2x right here?
Yeah. Times the x minus 2, that one?
Yes, you're flipping, and that's what you're doing. You're basically bringing this and putting it in the denominator here. Yes, I agree with all that. Yes. Before I do it, though, I want to make sure everyone's okay with this. What we're trying to do is get the x minus 2 to cancel, right? That means we need an x minus 2 somewhere else. Do you have an x minus 2 somewhere else? Not quite, right? So what Samuel was saying, right, was that this is the same thing, right? That's a fraction over a fraction. And so I could on my next line write, and notice I'm keeping the limit out the entire time. I'm never dropping the limit until the very end. Just keep the limit here. I'm going to rewrite this as 2 minus x over 2x times, and then this would flip and do the reciprocal, so 1 over x minus 2. Is that what you were saying, Samuel? Basically, the bottoms are going to multiply together. Yes, but I'm not going to do it because this is the part I'm trying to get to cancel, so I don't want to complicate it by passing the 2x through it. Does anyone see what cancels here? 2 minus x and x minus 2 are almost the same. They're not the same, though, right? That's right. We're going to pull a negative 1 out of the 2 minus x and make it a negative 2 plus x. So we can always factor a negative 1 out of something, right? And that changes the signs of what's there. So I'm going to make this, because I wanted a negative 2, I had positive 2. I wanted a positive x, I had a negative x. Since these differed by a sign, I pull a negative out. Now they match exactly the same, right? And now I can cancel them. But there's a negative 1 out here. That's kind of the give and the take, right? I was able to get them to cancel, but I had to include a negative 1 now. So here's where I am. Limit x approaches 2 of what? Negative 1 over 2x. And now, hopefully, it's fixed. We've gotten around the 0 by 0 over 0. What do you think?
Yeah.
Yeah. What is it?
It's going to be
Negative 1/4, right? Negative 1/4. Negative 1/4. So if I were to graph this, when we approach the x value of 2, your y value should be getting closer and closer to negative 1/4. Are there any questions on the algebra in this? There's still nothing crazy that we've done algebraically, right? This is nothing totally out of the ordinary when it comes to algebra. These are all things that I know in 1414 class you do. All we're doing is at the very end, we're adding the whole idea of the limit to it now, you know? All right, so we go a little harder now. Limit x approaches, let's go negative 5. We haven't done a negative yet. Square root of x plus 9. Oh no, hold on. Yeah, that'll work. Minus 2. No, 3. Sorry. Wait a minute. Hold on. 5, negative 5, 4, 2. Yeah, that's right. X plus 5 down here. That should cause some significant problems. So try direct substitution first. You getting 0 over 0? Okay. As soon as you see 0 over 0 now, you should be thinking that you're going to do something, right, algebraically? or trig. Still haven't had that yet. Got to build up to it though. So,
You can't separate the radical, right? We square root of x plus
no,
square root of
no,
nine.
can't split that up. Yeah.
But you could make two separate fractions, but I don't know how that would help.
Yeah, you could do like all of this over that, all of that over that.
Can you square the square root?
Can you square the square root? Not exactly. I mean, you
could write
can't.
it as an exponent.
You could write it as 1/2 power on the whole thing.
Oh, yeah.
You could do that. But you can't just arbitrarily square it, though. You couldn't do that because, I mean, that's like if you take a number and you square it, it's not the same number. If you have an equation, you can always square both sides, but we don't have an equation. So we have an expression, right? So let me see. What's that?
Could you
I heard it.
multiply the reciprocal?
I think I heard it. Reciprocal, no. I think that was that Samuel? He's not going to say anything? No, it's too late, Samuel.
What are, now, I was just gonna ask, what are we trying to do right now?
You said conjugate, didn't you? Did you say conjugate?
I was gonna say something like that, yeah.
Did you say conjugate? Okay, that's correct. All right. So, hey, sometimes you stumble upon it. I mean, that's a good thing, okay? Because at least you're thinking conjugate. Do you remember that whenever we saw like square roots, two different terms, and we were rationalizing denominators, that we would come in with conjugates? You know, we try and do that. Well, look, the conjugate is in our bag of tricks, right? I mean, I don't know if this really qualifies as a trick, more than just, it's algebra, but it's not very natural. It's not something that we would look at this and go, oh yeah, sure, let's just throw a conjugate at this. Because the conjugate, the purpose of it in the past has been to get roots out of the denominator, hasn't it? We don't need to worry about that because we don't have a root in the denominator. You see what I'm saying? But let's see how the conjugate might help us. I'm going to multiply by 1. What is the conjugate of the numerator? Square root of x plus 9 plus 2, and then whatever you do on the top, you have to do on the bottom. And I'm also going to point out that my hope is that x plus 5 at some point cancels. Because isn't this the part that's causing division by 0? Yes, that is the part. So if I can get that to go away, then maybe things will be good. So we've got to multiply out this top piece and figure out what it is. And see, I keep my limit here the whole time. I will take off if you drop your limit before it's time. Okay? It's like leaving periods off of a paper you're writing. You know, just having a continuous sentence the whole time. It's bad grammar, bad math grammar.
Could you explain how you got the plus 2?
That's what the conjugate is defined to be. So when you have two terms, a plus b, the conjugate of this is a minus b.